Well, good morning. My son is here. I'd like to remind me a story of a mathematician, difference between a mathematician, physicist, and an engineer. So he got out, and in the hallway there was a bucket. He looked to the restroom, toilet, and filled it up. It was leaking. He brought 5-6 times. Half the bucket was leaking by that time, but he was able to put off the fire. The damage was about $500. Then there was a physicist. His office went on fire. So he went to the hallway, same bucket with holes, and he started looking at the diameter of the hole, and then the pressure of the water, and made some calculations by the time he would come back, how much would be left. So it took him some more time, and he did about 10. Then there was a mathematician. His office went on fire. He went to the hallway, same bucket or partial differential equation. So no, it needs partial differential equation analysis. So he tried to set up a partial differential equation, and then looked at the partial differential equation, and then he says, well, there is a bucket, there is water, and this partial differential equation solution must exist. And by that time, the whole office was burned totally, and the damage was total office fire. So that's the difference between an engineer, physicist, and mathematician. Engineers always look for dirty and quick solutions, but find solutions for the benefit of the society. Anyway, that said, I'm Paul Mehta. I'm from Bradley, and I'm here to present this paper entitled Application of Waste Heat Recovery in Automotive Manufacturing Related Industries. Before I start my presentation, I have to make, with the permission of the chair, 2-3 observations. I have attended this TMT conference. This is the second time, but I always look at the program. And last night I scanned through approximately all the papers being presented at this time. Professor Ekone pointed out to the quantity of the papers year by year, but I personally submit that it's not the quantity, it's the quality. And last night when I scanned through, definitely the quality of the papers is excellent. And my conclusion, based upon this analysis, the focus was only on the top 4 or 5, at the most 6 pillars for various applications of heat recovery. As we know that waste heat has several applications, and in this case a systematic approach was used to select the candidates for using the recovered waste heat in an optimal way based upon financial and technical feasibility for the following applications. There are several, but in this case, after analysis, it was decided to focus only on heat recovery for applying to space heating, or heat recovery for preheating the intake air for these very pillars installed. The first application for, if we go back, and whether it is feasible to use this waste heat for space heating, that will be depending upon the local location of this kiln. Only 6%, if you read the paper, only about 6 to 8% area is dedicated to the office work. And then the geographical location of this kiln was next to the office. But however, in the paper it has given month by month operation and idling time, etc. of all these kilns. So it was found out that number one, the energy used for space heating is very small. That means in winter, when space heating needed, if at that time the orders are low and this kiln is out of operation or is idling, then naturally that was not possible or was not feasible. So economically it was feasible, but based upon other factors that was rejected, that it could not be applied for this application. Then the next application was for the preheating of intake air for these very kilns. Of course, this was a factory, and therefore the quality of the exhaust was not very important. If it has got certain pollutants, it is not supposed to be very clean, but that could be used. However, analysis was done based upon different efficiencies or incremental efficiencies of the heat exchangers available. The flue gases at this temperature, high temperature, they constitute a very harsh environment. And therefore, any heat recovery device that has to be capable of withstanding heat up, and therefore only devices like ceramic wheels or radiative or convective equipment that can be used for recovery. The analysis are done considering the various efficiencies of these heat exchangers, 55, 65, 70, though some of these devices can have as high as 80% efficiency, especially if a part of the flue gas is recirculated as the intake air. So here it is shown, these board ladders show that TK1, TK2, then RH1, though they, have got high probability for recovering heat, but the payback period, because of the idling, because of the low economy and low orders in the year 2009, their payback period was more than accepted, 5.11, 4.1, etc., etc. So therefore, these, at this efficiency, these kilns were not candidate, but the other kilns where the payback period is acceptable in the range of 1 year, 2 years, 3 years, they were selected for preheating the intake air. And the paper is shown that by implementing this strategy for waste heat recovery, about 50% of their gas bill can be cut down from 350 to about 175, and that's big saving for the company, and that was going to be implemented by this manufacturer over there. Then the next thing was to analyze the feasibility of cogen. Cogen is of course using waste heat to convert this or use it to produce steam, high pressure, high temperature steam, and to run steam turbines to produce electric energy. For that, first of all, we have to calculate electrical load factors and thermal load factors. Electrical load factor, average kilowatt used, the total kilowatts over total hours. So average kilowatt hour used over kilowatt, peak kilowatt, and higher the electrical load factor, that shows that high time, for example, in this case, the annual average load factor, electrical load factor was about 0.7 or 70%. That means 70% of the time this plant was using the average kW demand over there, which is not bad, but though we all know that the load factor, electrical load factor of 1 is the best. That means there are no valleys or peaks on the load, and that's the best for the utility, and that's the best for the manufacturer to cut down on the demand costs. Next thing was to calculate the thermal load factors for each kiln. Now thermal load factor was the average 1000 BTUs per hour used by the kiln divided by the burner capacity, which is the peak thermal load for that particular kiln. And here are shown the thermal load factors over here. So 0.6, 0.64, 0.6, 0.5 they are acceptable, but less than 0.5 that were not accepted. That means then we have got the available times for the waste heat, they are not good overall in the year. Now, as I said, electrical load factor shows that the average kilowatt demand is approximately 69% of the peak demand throughout the year, and for the thermal load factor, the kilns with low thermal load factor should be eliminated, and thus the tunnel kiln 2, roller hot kiln 3, and roller hot kiln 5, they will be no longer candidates to be considered for cogeneration based upon these calculations. Detailed data is given in the paper how these calculations were made. Now next was to calculate the thermal load factor over electric load factor. What is this parameter important for? This parameter is important that if thermal load factor over electrical load factor, they have high value, that means the timing when the waste heat is available and when the electrical demand is there, they coincide. There is no use to convert waste heat into electric energy if at that time there is no need for the electrical energy. So this ratio, higher the ratio, more is the coincidence at the time where waste is available and where the electric energy is required. If it is a low ratio, then naturally either the utility company should be available, should be ready to buy your extra electric power, or it is of no use and a big investment cost that cannot be recovered. So many plants have got cogeneration possible, but because of these ratios not very acceptable, they cannot implement cogeneration over here. So in this case here, dash 3.49, 2.5, 3.81, they were acceptable. So on the basis of this one, RH3 was eliminated. Similarly, RH5 may or may not be considered for further over here. The maximum ratios are given over here. So dash show TK1, TK4, TK2, they are great candidates for cogeneration. As I said, the annual average thermal load over electrical ratio, that is the annual average and 1000 BTUs hour demand over the annual average kilowatt demand. And this average thermal over electric load ratio, 1 MB, which stands for 1000 BTUs, or you still are in the system, but that's how still the utility companies sell gas over there in terms of 1000 10 to the power 5 BTU. This is just a unit for billing. So for the various killers over here, average BTU per hour is shown, and then average 1000 BTU per hour is shown, average kW demand is shown for the plant, and then that ratio is calculated over here. Now as shown in this table, the annual average for TK1 shows the best thermal over electrical load ratio, thus being the best candidate for cogeneration. Now not only it's important for cogeneration that the timing of the waste heat available and the electric energy demand, they should coincide. Even if they coincide and there is not enough energy available as energy content of the waste heat, then again it is not going to be economical feasible, because then the electric energy produced, that is very small in amount and not much saving, and therefore the investment cannot be recovered. So as shown in the table, the annual average for TK1 shows best thermal to electric load ratio, thus being the best candidate for cogeneration. Unfortunately, it may not be enough to fit the requirements for a cogeneration unit. Facilities that have a thermal load over electrical load ratio above 5, they are generally good candidates, and above 10 are the best for coincidence of the availability and the demand. But the best T over E load ratio for this facility is only 2.76. This is below the minimum as a feasibility parameter 5 requirement. So even though this analysis shows that it may not be a good investment, some of the numbers for this TK4 or TK1, that is the total energy used. If you look into the gas bills in the paper, you will see that from December onward for this year for the following 12 months, rather than the gas consumption increasing in the winter months because of heating, and rather than increasing, it is a rapid fall in the amount of gas used. And that is when the economic conditions went bad, their oral went very bad. So in reality, that year data was not the best data to analyze, because the economy, this is not the true representative. If the economy goes up and if the demand goes up, if the orders go up, then this may become feasible for cogeneration over there. So therefore, to sum up, even though this slide shows that it may not be good investment, some of the numbers provided by the facility may not reflect the overall profile of consumption of the facility due to lower demand for goods from the economic downturn. Cogeneration opportunities may become available for this plant if the production increases, and thus more data regarding study loads becomes available. So to conclude, a manufacturing facility which manufactures components effectively for the equipment used in automotive industries was assessed for energy efficiency through the application of waste heat. FAST, which is a very important tool, again, was used to study the energy consumption patterns of the kilns, and it has been shown that although a lot of waste heat was generated by these kilns, only a few applications were found to be technically and economically feasible, and if the economy improves, some other applications could be there. That concludes my presentation, and I have got to make two more observations about the conference papers. There were very good papers in machine design, kinematic dynamics in this conference.
Thank you very much, Professor Mehta. Okay, now we have coffee break, but we will take a few minutes of coffee break for discussion, common question for our keynote dinner in the restaurant here in the hotel on the opposite side of this facility of hotel at 8 o'clock. We will have a performance of music group and dancer characteristic for just public, and there is no doubt about the quality of the food as you heard this morning. And I would like to announce the authors to be in time before the station, and just keep on. Thank you very much once more again.